Yeah, but it's not, you don't have to start again, seamlessly forwarding, yeah. Yeah, it is. 5 minutes. See, we'll see young people much better than. Yeah. You want more? Yeah, I'll just do it. Но он тебе сказать, что он никогда не отвечает. А люди убедятся, что он maybe we should just start and people will be coming. So we have today here first lecture of Hermann Nicolai, the director of Albert Einstein Institute from Potsdam, which is Max Planck Institute for Gravitational Physics, right? Mm-hmm. So the lectures will be about applications of Kac-Moody algebras to gravity and supergravity series. Right? This is the first lecture. It will be all other lectures tomorrow at 5 o'clock, day after tomorrow at 5 o'clock, and on Monday at 5 o'clock. They'll be on the third floor in the room 311. All other 3 lectures will be on the third floor. Yeah.
Okay. Well, first of all, thank you for the invitation. Thank you for the introduction, for arranging this visit. As Ingrid said, this is going to be a series of a set of lectures about the connections between supergravity, gravity, modern developments, and the theory of the Kac-Moody algebras. And just to give a brief summary of what we can expect. So the first thing I'm going to do is I'm going to tell you about the BKL. And well, BKL stands for Belinsky, very famous Russian physicist. And this is about a certain approach or description of cosmological singularities. And this like and this generalization will consist in going much beyond what they did in the original work, because in the original work it was concerned with, mostly concerned with Einstein's theory in 4 dimensions. And as you will see, this picture can be beautifully generalized to any dimension, any kind of matter coupling to Einstein's theory. So then I will try to exhibit the link with Kac-Moody theory or Kac-Moody algebras. And this has also something to do with what's called hidden symmetries in supergravity. This is a very old subject, but it ties in with many modern developments, in particular duality in symmetries in string theory. You may have heard about duality symmetries in string theory, and that they play an important role in recent developments. Now, the main feature here, of course, is that these will be infinite dimensional Kac-Moody algebras. And I've been told that there are some experts here on Kac-Moody algebras. Are they here, or?
Some years.
Some are here. But from what I understand, this expertise is mostly about what's called affine Kac-Moody algebras. This is the Kac-Moody algebra type that's linked to current algebras and so on. Things that are, of course, very important in string theory. But my main topic will not be affine Kac-Moody algebras, but something called indefinite Kac-Moody algebras. And one of the nice things about indefinite Kac-Moody algebras is that basically no one knows what they are. So there's a real challenge here. This problem has been around for 45 years in mathematics. When Kac-Moody algebras were first formulated this theory was first formulated in 1968 by Victor Katz and Robert Moody independently. And since then, in this direction, there has really not been much progress. It is therefore all the more fascinating, I think, that coming from a completely different corner, supergravity, string theory, and so on, that we now discover hints of such a huge symmetry lying behind Einstein's theory and its generalizations. So the third thing is then, but this is really at the level of a project. This is certainly not a finished result in any sense. Try to exploit these links to find out what M theory really is. So I'm sure you've all heard about M theory. Has everyone heard about M theory?
Everybody.
It's this, this mysterious non-perturbative formulation of string theory that no one knows how to set up, and so people talk about it. And when you go to a typical conference, everyone will be talking about M theory, but it's a typical example of people not knowing what they're talking about. It's in fact, there's very little at the moment guidance as to what it could be, but the idea underlying this approach is, of course, that we want to exploit symmetry principles. And as you know, symmetry has been an extremely important principle in formulating physical theories. We think about general relativity, the modern standard model of particle physics, and so on. So this is clearly very important. Now I should say, I have a sort of program here, but it's really more important to me that I get across the message. So you are certainly welcome to ask questions at any point and to interrupt me at any point. If there's anything you don't understand. As I said, the important thing is not technical details, but the main message. And for the details, I'll just give you 2 or 3 references where you can look up, these are review papers, not the original papers, where you can find this. So this is work-based on a collaboration with people that you Martin, myself, of course. And this is, maybe I'll just give the archive number, that's probably enough. This is a review that was published in Classical Quantum Gravity, but this is HEP-PH 2002, 12256. Then I have something with Thibaut, well, maybe I should also add Axel Kleinschmidt, and simply list, because this was done in various combinations, then simply give the other references. So there's another review.
Hermann, is that number head TH?
This is at TH because
you better spell it, because otherwise like your archive number will not.
So these two are sorry. So this is head TH slash this and this. Actually, I don't remember when they started calling it archive.
2007.
2007. So this is. There's another one that probably has an archive number, but here only the journal reference, which is E17. So that's from 2008. 5 to 5. The last thing I want to talk about on Monday actually is a little bit disconnected from this, because this goes a little bit more into the mathematics. This is very on Monday, then very recent work, and this is actually something I would like to start discussing with some of the experts, because this has to do with what we call maximal compact subgroups of these Kac-Moody groups, about which very little is known. Okay, so this is the program, and so I would like to start out with this topic, and this will keep me busy for, I guess, 2 lectures or so. So PKL, as I said, stands for, let me try to get this right. Oops. Correct?
Yeah. Yes.
And Lifshitz I don't write out because it's so famous. So this is work actually that you can read about in Landau Lifshitz Volume 2. It started out originally with just a collaboration of Khalatnikov and Lifshitz in the early 60s. And at the time, and this is also interesting to read when you look at Landau Lifshitz, the book, you will see the view that they were taking in the early 60s. Namely, this was about question of singularities and general relativity. And there they write that the Schwarzschild solution, which is the quintessential solution of Einstein's equations, the singularities there are just an artifact of the theory of symmetry. And they wanted to somehow prove that singularities in general relativity are not generic. And this was about at the same time when Hawking and Penrose in England proved the singularity theorems. This is Hawking Penrose. Well, I don't have to write this out, but this was about 1968 or so, where they showed that under very generic conditions, the solutions of Einstein's equations will always evolve and become some kind of singularity. Like we see when you look outside with the telescope, we think that there are now black holes all over the place in the universe, and those are really singular solutions of Einstein's theory. Now, these singularity theorems are very general, but they don't give you a very detailed description of, you want to have a more microscopic or more detailed description of the singularity. And it is in this context, and PKL then went on. Well, PKL finally did. This came then in 1970. Was an approach to gain a more detailed understanding of the singularities. Now, there are all kinds of singularities in general relativity, but this word is related or restricted to what's called space-like singularity. And without going into the technical details too much, what does that mean? A space-like singularity is a cosmological singularity, and that's the kind of singularity we find at the beginning of our universe. And it's also the kind of singularity you will meet when you move inside a Schwarzschild black hole. So just to draw a picture to get an idea what this is. So let's just draw a picture of a Big Bang space-time, like our universe. So, well, of course, we choose coordinates appropriately, and we'll use. So we take this is the space-time, and we'll slice the space-time into spatial hypersurfaces that evolve in time. That's one way to understand cosmological solutions of Einstein's theory. You can think of this as being a description of a spatial geometry at a given time, and as time goes on, this spatial geometry evolves. This is what we see in when we're being outside, looking into the cosmos. So what you have is a sequence of space-like hypersurfaces, and one can choose time coordinates such that the Big Bang hypersurfaces are located at t equals 0. So this is the Big Bang hypersurface, spatial hypersurface. So this is the beginning of the universe, and then one can draw world lines of stationary observers freely falling like this. And so this is singularity. Color them out here. So, and the fact that this is singularity means that you cannot continue the space-time beyond. So it really stops here. And now, what you do is you draw light cones. Now these light cones are of course bent in some sense, and maybe they don't have to be straight light cones. And for each world line, and go back to the initial hypersurface, like this, and so on. So as you move away, you will be able to see much more and more of this hypersurface. But as you can see, as you get closer to this initial hypersurface here, you see that the spatial points decouple. So if you draw the light cones like this, it just means that these points, the closer you get to the initial singularity, are no longer in causal contact. This, by the way, is one way to characterize space-likeness of a singularity, because space-like was time-like, you somehow measure, you need the metric, but on the other hand, you think, well, the metric here on this hypersurface seems singular, and therefore it's kind of a little bit hard to define. But one way to define it is that as you take a hypersurface close to it, and then the points start to decouple causally, then the singularity is space-like. There are also time-like singularities or null singularities, but this whole theory only applies to this kind of situation. Okay, and this is, by the way, also related to this famous horizon problem that gave rise to the theories of inflationary cosmology. Because if you think, for example, if you take this to be the time where the C and B picture froze in the sky, this is like 300,000 years after the Big Bang, we have a frozen picture of the, if you just look at the temperature in the sky, and then it turns out to be the same in all directions up to 5 digits, and then there's immediately this puzzle: why, how can these 2 points be exactly the same temperature if they're causally decoupled? That's the horizon problem, but the horizon problem only was considered in 1978 or so, when inflation came along. So this work was clearly before. And horizon problem was not in some sense the concern of the needs of development populations. Rather, what they said or hypothesized, so EKL hypothesis is there. So what did they say? They said, so we have space-like similarity, and this is equivalent in some sense to causal decoupling, of spatial points, which is such, by the way, that as you approach, once you get very close, then each point, there's no more way to communicate even between points that are very close to each other. And this led, so this is the observation, this led to the hypothesis that in this limit for t to 0, this proper time, as you approach the initial hypersurface, spatial gradients, let's say dx, roughly, so this stands for spatial derivative along the spatial hypersurface, become negligible in comparison to time derivatives. So this doesn't mean that spatial gradients cannot blow up. They also go to infinity, but they go to infinity much more slowly than time derivatives. So in this way, you can see that you get, by making this kind of analysis, you really after more detailed description of what, the elements of the metric, how they behave as you approach this initial hypersurface. So this is the hypothesis, and if true, and by the way, I should say this is a hypothesis. Strictly speaking, I will tell you in what circumstances it can be proven, and the more interesting cases where it has not been proven. So this means that if it's true, it means that Einstein's equations, of course, Einstein's equations are very complicated, probably the most complicated system of partial differential equations in physics. But this leads to a drastic simplification in theory as t goes to 0. Okay? Because it really means that in this limit, in some sense, to maybe make precise, this partial differential equation reduces to continuous superposition of ordinary second-order differential equations. So that was the hypothesis they made, and I will tell you later that by making this hypothesis and investigating whether it's really true, they made a rather startling discovery. So, from this you conclude that if the hypothesis is true, then life should become very simple. Einstein.
So this, you're talking about time derivatives of the metric mostly, or other fields in the theory?
Well, actually, this also would apply to other fields, but at the metric. So let me see.
So what does that have to do with the Schwarzschild solution?
Well, the question is why when you fall into the black hole, it turns out that the singularity is also space-like. But
It's stationary.
Well, this is of course supposed to describe. Yes, it's true. One starts out with some stationary solution, but if you fall in, you sort of small perturbation to this, and it's sort of meant to tell you what's going to happen to you. Well, I will get to this. Okay. So this leads to us first to consider a one-dimensional simplification or solution of Einstein's equation, which where the metric just depends on the time coordinate in this suitably chosen coordinate system, and this is the so-called Kac-Moody solution, which was already discovered in 1926. Okay, so I don't have to write the Einstein equations because we're going to go into more detail later on. But the Kac-Moody solution is a very simple solution. You can write it here. So you make the following metric ansatz minus dt squared, so this is proper time, plus, and then the solution turns out to be of the following type in 4 dimensions. Dx 1 squared or dx squared plus t p2 and y squared plus t 2p3 and z squared. So we just have a 4-dimensional space-time with spatial coordinates x, y, z and time coordinate t, and then the solution takes this form that you have the spatial line elements, and they're multiplied by a factor of t to some power, which means that as you, in some sense, it means that spatial volume shrinks as you go to.
So this is an ansatz which you can plug in GR equation for motion and find the powers P1 and P2. And
yeah, I'm just going to say that. So you take this ansatz.
And the physical meaning, as you say, is just x is
in
one way.
You will see. You will see. Anyway, when you take this ansatz and plug it into Einstein's equations, then it follows that this solves Einstein's equations, Einstein field equations, if two conditions are met, and the following ones. This is easy to check, and we will see this a slightly different interpretation of this in a moment.
Is it okay to put 0 for solve?
You mean for the off diagonal?
Yeah.
Oh, the 0. Wait.
If I put all the p's to be 0.
No. That's not the solution of this equation.
It won't solve the
No. The Einstein equation, strictly speaking, there's a gauge choice, but the essential condition is well, it can be written in a different way, but this is essentially when you substitute it in the equation in the Einstein.
What is Minkowski space has to solve, but it is not seen as a solution. Minkowski space would correspond when P1, P2, and P3 are 0.
Yes, and you say that it's not on this.
Oh, of course Minkowski space is the solution, yes. Yes. Correct. Yes.
But it's not within this.
It's not within this class. Okay. So, so this solution is, as you can see, is homogeneous. Homogeneous means it's invariant under spatial translations, but not isotropic. So you can also check that if you calculate the curvature, that solution becomes singular for t goes to 0. And what you also see is the spatial. Well, first of all,
Hermann, does it solve Einstein equation in the vacuum or with some energy momentum tensor?
This is a vacuum solution.
Okay.
So now you can also see that in order to solve this, that one of the p's has to be negative, and the two others have to be positive. And what does this mean? And the overall volume, the spatial volume, is square root g, or proportional to square root g. And that's the, so you multiply these three factors and take the square root, and then you use this condition, so this goes like t, so spatial volume also goes to 0. Which means that you actually get squashed as you approach the singularity.
But then it means that, doesn't it mean that in at t equals to 0 you have some surfs?
Some what?
Some surfs for. Is it? I'm trying to understand what kind of vacuum solution which has singular Riemann.
Well, it's in some sense it's like the Schwarzschild solution, because the Schwarzschild solution also.
So it has singular.
It's a little bit like the Schwarzschild solution. It's really a vacuum solution, but you know that you might want to think about it like like the Coulomb field where you put.
Okay, I see. But yeah, that's what I did. So it's a solution of R V equals to 0, but the Riemann tensor for this guy is not 0.
No, that's right.
Okay,
yeah.
so
yes.
Minkowski's
it's just like Schwarzschild. The Schwarzschild you also have a non-vanishing Riemann tensor, but
so curvature is not 0.
Yes. So in this sense, it's singular. Well, really defining what a singularity is in general relativity is a rather subtle issue. So blow up a parameter is the first sort of approximation to this. But you see that what's interesting here is the way you get squashed, because one of the coefficients is negative. It means that you get squashed in two directions and you get stretched in a third direction, but in such a way that the overall volume shrinks to 0. Okay, and now coming back to the BKL hypothesis, the idea is that this, and this is the idea about this spatial decoupling idea, is, and this is the BKL hypothesis, general solution near the cosmological singularity behaves like Hasner, but with Hasner coefficients that depend on where you are. Okay, because if you just look at the part of the equation where I know there are no spatial derivatives, you can choose this p as you like at each point, and therefore you might say that this is the kind of leading behavior of the metric as opposed to singularity. Now, of course, this cannot be an exact solution of Einstein's equations because you've neglected the spatial gradients. But the idea is that the general solution behaves like this. It's dominated by this up to controllable, in some sense, level of corrections. So one way to prove this, and there's certain spatial configurations where this can actually be proved rigorously, is that as you approach the singularity, this is the leading behavior, and then you have sub-leading corrections that you can calculate by substituting this ansatz in the Einstein equations and making some kind of expansion. So this was the idea, and in this way you already see that you have a more detailed microscopic control of how the metric behaves in the vicinity of the singularity. This is more detailed information than what you can get out of the Hawking-Penrose theorems. So this was the hypothesis, and in fact, this part of the story, as I said, you can read about in Landau-Lifshitz volume 2, this is the last chapter that at least when I studied Lambda Lifshitz, I never got to. Somehow it's called on the fate of the cosmological singularity or something, and this describes this time. Now they said it's a hypothesis, but we really need to check whether spatial gradients do become small as we approach the singularity, because this is something we have to check. And of course, it's not something you can check. You need a little bit more input in order to check this. With this ansatz itself, you cannot check it. And therefore, they had the idea of sort of slightly generalizing this in the sense that they generalized these line elements to be the line elements of a spatially a constant space of negative of a space of constant but non-trivial curvature, the spatial part of it. And so they test, this was PKL again, test hypothesis with a homogeneous curve, homogeneous curve spatial geometry. And this is what's in the literature referred to as Yankee models. There are various kinds of Yankee models. But the details don't matter. Anyway, we have a different way. We'll get a different way of dividing this. But what they found by doing this, and it's again explained in volume 2 of Lambda Lifshitz, if you make this slightly more general ansatz, and you substitute it into the Einstein equations, and then you follow this evolution, and it turns out that in fact, not always are the spatial derivatives smaller than the time derivatives. As you follow this, and this is because, as I said, one pi has to be negative, so it is plausible that as you follow this evolution, you see that at some points that spatial gradients will become non-negligible. And then what happens, and this they did by, and this is again something we'll find a little bit later, in this approximation they found that, well, maybe I just write it in words, that in this transition regime where the spatial gradients become large, you have to take a closer look at the equations. And then what happens is that you have to switch from one set of Kasner coefficients or exponents to another set of Kasner exponents. And this is what they refer to as Kasner bounds. What it means is,
how do you transform what?
You will see this. I will, the using is of our method is that there's a much easier way to understand why this happens and how it happens. I just want to describe in words what they discovered. So what they discovered is that the solution, making this slightly more general ansatz, sort of behaves like this for a while, and then you have to sort of switch to another regime, and this corresponds to a change in these coefficients, again satisfying these conditions, and this is referred to as the Kasner bounds. So the dynamics near singularity, near the singularity is a sequence of Kasner flights and Kasner bounces. Which means that you approach the singularity, for a while it behaves like this with some set of coefficients, and then you have to switch to another set of coefficients. This is then the Kasner flight, and then it bounces again and so on. And at this point, there are two kinds of possibilities. There are two possibilities. As t goes to 0, there are two kinds of possibilities. Either this happens only a finite number. And remember the picture here. So here's the time axis, and we're sort of we're going backwards in time towards the singularity. So you say time equals epsilon and time equals 0. So you go back, and there's this Kasma bounce, and it may happen that this is possibility number 1, only finitely many bounces. Which means that there's a last bounce as you approach the singularity, and then from then on it will be like this, it will behave like this.
So do I correctly understand, sorry, I just, when pi's become functions of x,
yes,
and when the slices are not necessarily flat, when you approach the singularity, pi's like flip.
They can flip, yes.
They change.
But there's a question, do they flip? How many times do they flip until you reach the singularity? And there are two possibilities. Either they flip only a finite number of times, and this is what in general relativity is called AUD, asymptotically velocity dominated.
I'm sorry. Why do you suppose that I should flip not smooth? Why it can change smoothly? Why there are only constant?
It's not assumptions.
The parts with constant PI and then.
You mean constant as a function of time?
There are functions PI from x. Why it should flip non-smoothly?
Well, it will flip. No, it will flip smoothly. But the question is, how many times does this happen?
Vale, this is not an assumption. This is a statement. What happens if you solve Einstein equation? You see these two options.
You have the two options. It's either this or infinity many.
Assumption is the answer.
Many bounces. Infinitely many bounces. And this means that this is what's referred to as chaotic oscillations of a metric. And I think Belize BKL originally they had expected that this would prevail, but to their surprise, I suppose, they discovered that in Einstein's theory, gravity in 4 dimensions, actually you show that this occurs an infinite number of times as you approach the singularity. So that means that, so this is the situation where you can prove rigorous theorems, where you can make an ansatz and show that it remains like this as you go towards the singularity, and so it's this up to subleading corrections, or otherwise, in this case, which is the much more interesting case, this sort of this Kasner behavior is there, but the Kasner coefficient is with an infinite number of times. So what does this mean? Because this is also relevant as you approach the singularity of a black hole, you fall into the black hole. Yes, of course you will get squashed, but you will get squashed in a very interesting way. Namely, as I said, there's always one that's negative. So in one direction you will get stretched, the other two will get compressed. But the number of directions for this, the directions in which this happens, flip an infinite number of times before you fall into the singularity. So it's really like a cosmic mixer. And this is why it's been referred to, this whole picture, by Misma. He has invented this word mix master universe. And one way to think of it, you kitchen, you have this mixer, but it's really a very bad mixer.
This is what Manin was talking on 2nd of September.
What the mix master universe? Yes, it's related to this. Now, the question, of course, what kind of theories have which behavior? And it turns out that whether you have this possibility or this possibility depends on what kind of theory you have. So if you have pure gravity, Einstein gravity, this is chaotic in this PKL sense. For space-time dimension b equals less than 10. So if you formulate Einstein's theory in 11, 12 of mod space-time dimensions, it will actually have this behavior. And we're going to see how this comes about. And then of course there's the question, if you calculate matter, can you suppress these chaotic oscillations or not? For example, what will happen is that if you couple a kiloton gravity, so when you couple this Einstein theory to scalar field, suppresses. How is it suppressed? But, and this is perhaps the most important observation, is that if we think about the theories that we get from string theory or supergravity, all the theories that we sort of look at in the context of unification and quantum gravity, all these theories are such that chaos prevails. For example, you've heard about 11-dimensional supergravity. That's the maximum number of dimensions where you can formulate a supergravity theory. So if it was just pure gravity, then it would not be chaotic. But in 11 dimensions, in order to get the supersymmetry, you need an extra 3-form field, kind of photon, 3-index photon, and that field reinstates chaos. So all the low-energy effective theories you get from superstring theory or supergravity have the feature that they're chaotic. So let's put this somewhere. Superstring effective theory, which is some supergravity theory, always chaotic. I mean, at least the theories that we think are most interesting. So, now, as I said, to understand this more systematically, you can either try to do it the way it's done in Lifshitz, which is kind of not so easy to follow, I would say. Or, and this is actually where this Kac-Moody connection comes in, because we will sort of reformulate the problem and thereby find a connection to these indefinite Kac-Moody algebras, where this behavior can be modeled in terms of what we call cosmological billiards. Just to give you the catchword, this is something that takes place in the so-called wine chamber of this Kac-Moody algebra. So let's now go back and start again to sort of understand this thing in a more systematic fashion. You see, this result originally was derived by the people in Brussels, well, certainly 25 years ago. But it's a rather intricate argument to show that for beyond 10 dimensions, the solution of Einstein's equations does have this more regular, controllable behavior. So let's therefore go back to Einstein's theory and mention this general things. How much time do you have?
Well, as a general, there is no limit,
but in reality there is a limit, and what is the limit?
Let's say
whenever he starts yawning or sleep or walking out of the...
Let's say you have
because I already see that it takes more time than I originally intended. So Einstein's equation, so general case. So what we want to do is we want to take this description, but we do not want to simply drop all the other terms in the Einstein equation as you do when you go to the Kac-Moody solution. But the idea is rather to single out the diagonal parts of the metric, which are the ones that appeared in the Kac-Moody solution, and develop a kind of effective theory for them, where the effect of all the other degrees things that appear in Einstein's equations, which there are, of course, spatial inhomogeneities. Which really means that you cannot ignore the fact that the actual solution does depend on the space coordinate. Also the off-diagonal components of the metric components, and finally there are matter fields to which the theory comes. All these will have an influence on the actual behavior of the metric, and they all contribute to the question whether the solution is chaotic or not. So let's let me first discuss the Einstein equation in slightly more general context. Let me just see. Yeah. So as I said, we're going to proceed from the ansatz, and we always do this at one particular point. So the idea will be to single out at some spatial point, because we go to some spatial point, single out diagonal metric degrees of freedom. And determine and define some kind of effective field theory or effective theory for them. This is a little bit in spirit like what you have in quantum field theory, when you have heavy degrees of freedom and you integrate them out, and then you write an effective theory for the low energy degrees of freedom. So this is a little bit, it's not the same quite, but it's in a similar spirit, where one singles out the diagonal degrees of freedom and then sees what does the rest of the theory do to them. So let's again start with a metric ansatz, but now a little more, slightly more general. So let me see. So we're going to write this like this. I'm going to make a more general ansatz. So in the Kac-Moody solution, this was put equal to 1, but this is so-called lapse function. You can choose a gauge for this.
It's functional time only?
No. It's going to be, in principle, it's meant to be a solution. It's metric depends on space and time, but we're going to analyze it in one particular spatial point. Yeah, this is important. I mean, you need to go beyond the Kac-Moody solutions in order to actually see this. Plus, and then we're going to write this as follows: 2dA, where A runs from 1 to little d. So space-time dimension will now be said is equal to capital D, and we set it equal to little d plus 1. So little d stands for the spatial dimension times theta A and theta A, where these are the theta A parameterizes the off-diagonal components of the metric in something we call Iwasawa decomposition. So this is something like NA, I or M, rather, dxm. So what one does here really for the metric is to write. It really means that this is the spatial metric. So this is in some sense the same as G and N, Gx n, Gxn, and these are kinds of frames. So one way to think of this is theta A is like a spatial field line. So, okay, so this here we have reinstated this gauge degree of freedom, which is a lapse. Here we've sort of separated the metric into a part that sort of parameterizes the off-diagonal spatial degrees of freedom, and maybe I should already say this. This is really originally this is a field bind, which is just an element. It's just a D by D matrix, an element of GLD. And for any element of GLD, we have what's called the Iwasawa decomposition. So let me call this G or E. Really, if this is an element, there's some matrix in GLD. It can be represented as, in the Iwasawa form, as G equals K, A, N, really. Where this is an element of the compact subalgebra, this is a diagonal matrix, and this is an upper triangular matrix. So this is element of SOD. Because here we're just looking at the spatial geometry. This is diagonal, and this is upper triangular. I call it curly A. I shouldn't let me call it B. Now, as you can see, you can take the metric by squaring this field line, and the general metric will have this form G equals N transpose A squared N, because in the way the field line are contracted, this is a Lorentz rotation, and the metric is precisely that contraction of the field line which is Lorentz invariant, and the local Lorentz group. And this is basically what you see here. So this is the upper triangular part of this matrix, and this is the diagonal part. So the diagonal part of the metric is characterized by these coefficients beta, and these are we refer to as scale factors or logarithmic scale factors. And as I said, it's meant to be the full metric depending on space and time, but we're looking at a fixed spatial point. So when you now substitute this into the Einstein action,
Which variables are depend on space and time?
no, in principle, to start with, they all depend on space and time. But we're simply looking at, we're now fixing ourselves to one spatial point. You see, the difficulty is, of course, to sort of glue this together to get a full solution of Einstein's equations, of course, that you cannot do. So in some sense, it's still an approximation. So if you now substitute this into the Einstein action, we find an effective Lagrangian for these diagonals. So if I ignore this for the moment, then I find an effective Lagrangian, which has the following form, up to factors, which in tilde times so I'll just take now the time derivatives, you get to write this as G, AB, BA, dot B, B dot, plus our things, of course, and this is a sort of effective metric on the space of these scale factors, and this has nothing to do with the effective metric, with the real space-time metric or spatial metric, but it's a sort of metric that appears on this space, and its form is determined by actually working out what this is. When you substitute this ansatz into Einstein's equations, and then you find it's B B A dot squared minus sum of BA.
Will you obtain this form even if betas depend on x also?
No, I'm simply neglecting at this point the spatial gradients. You see, this is an approximation where we sort of, in the end, we will simply take the full Einstein action, go to Hamiltonian formulation, not neglect any terms, but still look at this expression at a particular spatial point. So here the sum runs of all spatial indices, and when you simply, it's like a kinetic term that you get from the Einstein action, but restricting to these scalars.
The second term is squared, right?
Squared, sorry. So this is what you get, and since you probably have heard about the so-called the bit metric, which appears in the canonical treatment of Einstein's theory, it's simply the restriction of this bit metric to these diagonal scale factors. Okay. Now, one important thing about this metric is that it is indefinite. Indefinite signature. Signature is minus plus. So you see, this is so you can already see this is something completely different from the space-time metric, because we're sort of here looking at the part of the space-time metric which is purely spatial. So the spatial metric here is of course positive definite, but we're now talking about a different metric, namely a metric that lives on this space of diagonal scale factors, a space that's coordinated by
So it's not necessarily positive because it's M here.
Oh, this. No, this I will write out later. What this gives extra contributions to the Hamiltonian or Lagrangian. But in the first step, we're now setting this equal to unity, and I just want to reinterpret the Casimir solution from this point of view. So here, the other thing which appears here is this n tilde. This is a really fine Lapse function. It's then the n divided by square root g. Well, square root g you can calculate from here. So, depending on what kind of situation, you still have the freedom here to choose this Lapse function. So now, as you can see, this is effectively, what is this? This is in this space, and neglecting all these other terms. This is actually like a free particle action, or Lagrangian, with an indefinite signature. So it's like, so we already see what's going to happen. And the other thing we get from Einstein's theory is not just an equation of motion for the data, but you also get, by varying this n tilde, you also get a constraint. Constraint. Okay. So what is this? This, in terms of these betas, when you see this, and you look up your again Landau-Lifshitz, when we talk about relativistic point particle, this is actually a relativistic point particle, because you get a second order equation for this, and on top of this you have this relativistic constraint, which is just like the constraint for a massless particle.
And where does constraint come from?
And this is the Hamiltonian constraint.
If you vary over M2, okay.
If you vary, it's because in this, you see, it's a constrained Hamiltonian system. So you have variables beta. They will, when you vary them, you will just get beta dot double dot equals 0. But on top of this, you have the equation which you get by varying the constraint. And this is exactly like the relativistic point particle. When you look at the formulation of the relativistic point particle, you not only get this equation for this beta, but you also get this relativistic constraint, which upon quantization just becomes the Klein-Boltzmann equation. So what is this? Effectively, what we find is the system, effective description in data space is the same as that of a free relativistic particle, except that the motion, the relativistic motion, does not take place in the real space, but in the space, in the fictitious space of these scale factors. You see, there's the space of space-time, but then there's also quantum field theory or general relativity. You also have the space of metrics or space of fields. It's on that space that all this takes place. And now you can see.
Excuse me, but where's Minkowski method here in for beta? It's where the sounds are Minkowski or what?
No. Well, then you would simply say that it's equal to 0.
This means that there is one specific direction, that is time, but which one?
Well, I still have to tell you, I wasn't very careful about. Right, how should I say this? When you have a relativistic point particle, it's a sort of x0, and you have the spatial axis. Okay, and when you solve these equations, then you get just the motion of a relativistic particle. You see, the thing is that in this theory, you have a freedom to choose the time coordinate. So there are different descriptions, and
so basically, M plays the role of metric along the time.
Correct. Yes, that's one way to view it. Because if you write this as a world line in some Minkowski space, and you write such an action principle, then this is really like an Einbein, or the metric has just G11 or G00, if you like, as a component, and the theory is invariant on the reparameterization of the time.
Yeah, and that is the reason you call it relativistic particle.
Yes, and this is actually the reason. This is always true that when you have such gauge invariance or time reparameterization invariance, then you always get a constraint in the associated canonical formulas. With this extra constraint that you get is for the particle, for the free particle relativistic, is just the time coordinate, the relativistic dispersion relation, if you like. This is what this is. Okay, so now I should also say this is something I glossed over a little bit. I think I should put this right now. Let me just say this. The solution of these equations is now simply V, because it's just a second order, it's just beta double dot equals 0. So this is the solution. And how is this related to the Carson solution? Well, you see, we've written this was originally t to the 2p in the original way I wrote it, but I'm now using a time coordinate which is appropriate to this. And therefore you can see that if you compare this to the original Carlson solution, you see that this tau coordinate is related to the original coordinate, proper time coordinate in this way. And this means that, well, this was proper time, where the singularity is located at t equals 0, and this variable, as this t goes to 0, this goes to infinity. So this is, I sometimes refer to this as a Zeno time coordinate, because this is a convenient coordinate, because as you want to analyze the behavior with the singularity, you sort of blow up the time coordinate to infinity, and in this way you get a much nicer description. So what I'm
But
saying,
how to see that tau is related to original time via this? Tau is the proper time, right?
t is the proper time.
T is the proper time.
This was the proper time. Proper
But
time.
does this T coincide with that time which is in that entry upstairs?
No, I mean it corresponds to a certain choice. This is the time coordinate that you get by choosing the gauge n tilde equals 1 or n is equals the square root c. It's a different choice of time coordinate, and but the essential feature here is that the time coordinate, the proper time goes to 0, and then you have the original form of the Carlson metric. But in this time coordinate, you blow up the time between epsilon and 0, you blow it up in such a way it goes to plus infinity. And as you see, a first nice feature is that in terms of this coordinate, I can describe the Carlson solution as you move towards the singularity as effectively as a free relativistic motion in this space of betas. So, so what I will tell you next time is, of course, this is of course still the Carlson solution. It's nothing more than that. So the aim will be.
But I actually don't see that it's okay, I see. No, okay.
So the aim is to develop an effective action to replace lambda L3 by something like G AB theta A dot theta B dot plus, and then something, or minus really, some effective potential that depends on the betas and possibly other variables, where this describes the modification of the Carlson behavior that's caused by these modifications. So to repeat, I've just told you that there's a simple way to recover the Carlson solution using appropriate coordinates. You can think of the Carlson motion as being, or the Carlson solution as corresponding to the relativistic free motion of a free particle in this fictitious beta space. And what will now happen is that once you take into account these other effects and in some sense integrating them out, this will effectively lead to modifications of Lagrangian by the effective potential. And in this effective potential, one would be able to describe the oscillations or Carlson bounces very effectively. It is at this point that.
Can you pinpoint at this moment where the Kac-Moody algebras will appear?
Not yet, because well, I can say it. Well, okay, you give me 2 more minutes just to give you a punchline. It will turn out that this metric that we get from Einstein's theory doesn't know anything about Kac-Moody algebras, turns out to be identical to the restriction. Well, first of all, it turns out that you can identify these betas with a Cartan subalgebra of some indefinite Kac-Moody algebra. Why indefinite? It means that the Cartan killing metric is indefinite. That's what singles out indefinite Kac-Moody algebras. So you make this identification, and then you can think of this being a motion in the Cartan subalgebra of this Kac-Moody algebra. And furthermore, what turns out to be, and this again kind of miraculous, if you like, that this metric that's computed from the Einstein theory turns out to coincide with what's called the Cartan killing metric of the Kac-Moody algebra, restricted to its Cartan subalgebra. So this will be, this is like the Cartan subalgebra. And before we move in the space of scale factors, but what I'm telling you is that this is effectively like a motion in the Cartan subalgebra of some indefinite Kac-Moody algebra. And then the modifications which appear here calculated from gravity, will turn out to be exactly related to what happens in the Kac-Moody algebra when you go beyond the Cartan subalgebra. If in the algebra, you have the Cartan subalgebra, but then you have the off-diagonal elements of this group, and when you switch them on, they will effectively be in correspondence with this effective metric that you get from analyzing Einstein's theory as matter and so on.
Thank you.